Okay, now let's talk about state functions. We can also classify properties as state functions. So what is a state function? Well, a property is a state function if it depends only on the state of the system at any given time and is independent is independent on the path on the path on the path used to get to that state or point in time. Okay, so that might not make a lot of sense. So let's go over that by contrasting it with what we call a path function. Okay, so path functions are dependent on the path taken to go from an initial state to a final state. So two common path functions are heat which has the symbol Q, and work. So we'll talk more about work in a bit. So work, you know, we might not love work like most of the time, but we gotta admit it does make getting through life a whole lot easier, right? So, but you should have a job and that you love, right? And it won't feel like you're working at all. It'll feel like you're kind of just doing a hobby, and it's your livelihood. So for me, that's chemistry. I know most people probably won't agree that it's chemistry for them, but just find that something you really love to do, and that it can be a viable source of income for you. That's pretty much kind of our responsibility as working citizens, people in the society. So, and doing this any kind of doing the work you enjoy, I think, is the most enjoyable way to pretty much live your life. But anyway, enough of these philosophical things. I just want to emphasize that if you work hard, you will get what your dreams will pretty much come true. So just work hard and don't give up, and just keep on going. So with hard work, you can achieve anything. All right. But also, what you want to achieve is something you should be passionate about, and it's not something you should, be like, oh, I have zero interest in. Because if you have zero interest in something, that's going to make it like 10 times harder to work hard. So, just kind of think about that. Just if this class, is not your cup of tea, just think of as a stepping stone towards what you really want to do. And so, it's important that way. So you kind of find that it's important, and I should probably try, do my best effort so I can, achieve what I want to ultimately get to. All right. So let's take, so now let's kind of go over why these are path functions. Well, the amount of work it takes to go from, point A to point B, right? So work is what we call force acting over a distance. So it's the amount of force required to, move box A from this point to that point in space. Okay? So the amount of work it takes to go from point A to point B will depend on what path you take, right? Like if I want to move this box up a flight of stairs, it's going to take more work to go up the stairs with the box rather than using an elevator, right? So we don't usually transport freight up the stairs because it requires a lot of work to do that. So usually we use elevators to help us transport heavy objects, right? So it does depend on what path you take, right? You can go the long way or the short way. So And if we're thinking about heat, right, the transfer of heat or transfer of energy, the amount of heat transferred will depend on path taken, right? So a longer path will most likely result in an inefficient transfer of heat and result in more heat loss. So you're going to lose heat that can be used to heat your target object or provide heat to a room. The longer it has to travel, if your system is not insulated, it can lose heat to the environment or the surroundings. Okay. So what's another example of a state? What's an example of a state function? Well, example is temperature. So say you have the temperature of water at some point in time. So the fact that it's this temperature, 75.1 degrees Celsius at some moment, doesn't tell us anything about the history of our system, right? It just tells us the temperature is 75.1 degrees Celsius. So it doesn't really say, okay, was it at originally 100 degrees Celsius and it cooled to 75? Or was it at 50 and it got heated up to 75, right? It doesn't tell us anything about that. It doesn't tell us anything before we take the measurement. So by that kind of logic, we can say temperature is a state function because it only tells us the state of the system at the moment we measure the temperature. So this allows us to measure the change in temperature because it only depends on the initial and final states. Now, if temperature depended, if the total temperature depended on the path, we couldn't use this this kind of boiled down equation, right? So the fact that it's a state function allows us to take the change in temperature. Okay? So usually if you see a change in something, change in volume, change in temperature, change in pressure, those are state functions. Okay? However, we can't really say that the same for heat or work because they are not state functions. So you'll never see the change in heat. Well, that's kind of a misnomer. What I meant to say, change in Q. You'll never see that. And you will never see change in work. But you may see change in temperature, pressure, volume, and stuff like that. Okay. So this is where we get our change in temperature equals T final minus T initial. And then we can also say total energy or the energy of our system is a state function because it only depends on when we measure the energy, right? Not the path it was used to get to that state. So total energy or energy in general, we can express that change E final minus E initial. Okay. All right. So now let's go over this analogy here. So suppose we have a crate on the first floor of a tall building, and we wish to take the crate to the 10th floor. Okay? To do that, we will have to expend someone's or something's energy, right? So it's either we spend the energy to lift the crate from the first floor to the 10th floor by going up a flight of stairs, or we use the elevator to do work to do that for us. Okay? So let's go over some of these terms. The energy of the crate will change because the crate's potential energy is greater on the 10th floor than on the first by an amount that depends on the mass of the crate, the acceleration of gravity, okay? So I wrote this equation, delta E equals mgh. That's that's pretty much how you calculate potential energy of an object that's moving or that's falling from a position that's above the ground level. Okay. And the last thing is the difference in height. Between the 10th and first floors, right? So ideally, what the only variable influencing the energy of the crate between those two positions is the difference in height, right? So it's the height. Okay? So now, if the crate was transported to the 15th floor, the energy of the crate would be, what would it be, larger or smaller than it was on the 10th? It was on the 10th or first floor. So it would be higher or larger. Okay? So how the crate gets from one floor to the other doesn't change the energy of the crate. But what changes the energy is the initial and final states. So the energy change by the crate only depends on the initial floor it started at and the final floor. Okay? Now, suppose we transported the crate to the 10th floor from the first floor and then return to the first floor. Okay? So basically, what would be the energy change of the crate? So we went from the first floor to the 10th floor. So let's say this is the 10th floor. Here's the first floor. Okay? And then we went back down again to the first floor. Okay? So we went back to the let's put the box here. Went to the 10th floor, and then now we're at the 10th floor. We went back down to the first floor, right? So that means so let's just say so the initial position. So delta x means change in position. So change in position. If you remember that from physics. Equals 0 because the position x final minus x initial equals 0 because they're both the same floor, right? That's the first floor, so the change in position is 0. So what we say is that the initial and final states of the crate are the same. So what we can say here is that the energy of the crate will not change. Okay, so we took the energy of the box or crate at the first level. We'll get an energy value, right, through mgh, the potential energy. And then once we calculate it again at the same level, we take the difference of those energies. It'll be the same. It'll be 0. So the energy of the crate will not change. Okay? So that's how we think about that one. So another example of a non-state function that depends on the path you take is when you drive a particular route on the freeway or highway, right? So say, you take this one pathway and then you take this shortcut. right? Both paths will lead you to the same place because you start at an initial point and you went to a final destination, which is doesn't change for each path. The initial and final points don't change. What changes is how you got there. So the in between the points is what matters. So both paths will take you to your destination, but the amount of time traveled and time spent will be different. So that's another instance of a non-state function, and that is distance. So no matter the distance, your initial and starting point will be the same. So it's kind of like what we're saying for energy. Energy does not depend on the path taken. It only depends on the initial and final state, because that's how we measure the change in energy of a system. Just what it started out with at one point in time and what it ended up in the second point in time. We do not care about anything in between, because that would represent a different point in time, and we're not interested in that. We're just interested in the initial and final point. Okay? So let's just say, you have a car here. And here's your destination. Here's home. Okay? So say you go a linear route here. And then say you take, so this is to say this is the fastest way, so it's probably the freeway. And here is another route you can take where it goes a bunch of turns. Okay, so maybe this is taking some back roads or some or some, long, windy route through some woods. Okay. So, the initial and final states are the same, but you see here, if we were to calculate the distance, this is a much longer distance. More time spent. So we're assuming we don't really need to consider the speed, but, it'll take a longer time to reach probably home, right? Because you have to travel slower, you have to go over a longer distance, so it's going to be a lot more time. Whereas in the freeway, usually you're going one straight route, and you can go pretty much faster, right? Right, so that's an example of a path function. Okay. All right, another illustration here of a state function is elevation. Okay, so pretend you start at the bottom of a parking lot, and then you go up to the top floor, right? The elevation between the ground level of a parking lot and the roof is the same regardless of where you take path A, which you drive upward, or if you take path A is where you use an elevator from the ground level to the top level. And you see here, the initial state 2 and state 1 is the same regardless where you start from path A or path B. Now, the distance traveled is going to be different, right? So path B will probably require a longer distance traveled, and you probably waste more gas, whereas path A will result in the shortest path, but you still reach the same point, okay? So we could say elevation is also a state function, because elevation only depends on the initial and starting point. But distance and work, not state functions. So let's just highlight that. Okay, so checkpoint here. Suppose a crate is dropped from the 10th floor of a building. When at rest on the 10th floor, what kind of energy does the crate have? During the fall, what kind of energy does the crate have? And what happens to the energy acquired by the falling crate when it comes to rest on the ground? Okay, so let's draw a little diagram here. So here's my temp 4. All right, so here's the temp 4. So the crate is at rest, right? And now it eventually drops to the bottom. Here it drops to the bottom here, and now it's at rest at the ground. So here's the ground here. Okay, so let's talk about what kind of energy each of these the crate has at each point in time. All right. So first, when at rest on the temp 4, what kind of energy does the crate have? Well, so it's not moving, right? It's supported by the normal force of the temp 4, so it's not going to fall. So what happens is the energy is going to be equal to just the potential energy. So we could call potential energy PE. So it's not physical education, potential energy. I don't remember the symbol for potential energy. So we're just going to call it potential energy, okay? PE. Now, as it starts falling, so it's not moving, right? The crate's not moving, so there's no kinetic energy. So all the energy the crate has at this elevation is potential energy, so stored energy. So now as it falls during the fall, right? So it's going to start falling. Okay? So eventually the energy, eventually, you know, the as the box is falling, so I'll give us some speed lines here. As the box is falling, the energy now is going to be the sum of potential energy, decreasing potential energy, and increasing kinetic energy. So eventually, potential energy will start to decrease and kinetic energy will start to increase because now the distance to the ground is now going to decrease as the box is falling. And as it falls per second, the kinetic energy is going to increase due to acceleration, right? Because for every second that passes, the box is going to increase its speed by 9.8 meters per second. So that's the force due to gravity. So the box will keep falling, right? And as the box falls here, it eventually gets to a point here where the box is now going to have more kinetic energy. Okay. Here, the potential energy is decreasing because the distance is decreasing between the ground and the box. And now kinetic energy is increasing. Okay. So what happens now is when the box hits the ground, right? So it's going to probably leave some, probably have some, you know, force to it when it hits the ground. So basically, all the energy the crate had, we can now translate it to. So here's the final energy of the crate. So maybe let's just move this over here. Oops. So we're saying all the energy of the crate now is gone. There's no more, and the crate has no more energy because it's now on the surface or on the ground. So the energy could be lost as energy gained from sound. So it produces a sound, right? You know, heavier objects, when you drop them, when they hit the ground from a really high distance or high elevation, they'll produce a sound, a really loud sound, and that's due to energy transfer being translated to air molecules, and the way those air molecules interact, they cause a sound. And then it could also be cause, you know, sometimes when you drop heavy objects, right, they make a dent in the ground, and that's because the force of contact, there's energy being transferred as heat, and that will heat up the surface that came into contact with the heavy object. And, you know, that heat can cause deformations And so if you heat something, right, the amount of energy that's used, that's transferred, could deform the other surface. So we can also say heat ground. Okay, plus work, and also plus work. Oh, sorry. I guess I meant to say work is what causes the end the hole. Maybe if you make a hole in the ground or make a dent in it, that makes much more sense because you can also just transfer the energy to heat the temperature of the ground, right? So that's what heat stands for, or that's heat transfer, raising the temperature of the surface. But what actually deforms or kind of makes a hole in the ground is the work, energy being transferred to do work, the amount energy is being transferred to kind of, the energy is not being used to heat something up. It's being, or raise the object's temperature is being used to act as a force against the surface. So that's what causes, like something to deform, or like to change shape. Is usually work, energy being transferred to work, and it's acting on the surface. So work around, this is what causes, make a hole or indentation. Now the box fall is so heavy that it's so heavy, and it hits a surface that is has much more mass than, or more density, I would say, than what the crate has. Then it can implode, right? Because when two things come into contact, right, there's the active momentum. So momentum, the heavier object will cause have a greater force of impact. It will make the force of impact will be greater on the smaller object than the bigger object, right? So, but that's kind of like too much physics we're getting to, so don't worry too much about that. Just worry about how, like, the energy of the crate, it lost all of its energy when it hits the ground, and what happens is, it gets transferred to sound energy, it gets transferred to thermal energy, and also gets transferred to, the energy gets transferred to do work on the surface or on the ground, right? Yeah, but maybe the best thing is to say make a dent, not indentation. Okay. All right. So now let's stop there, and in the next video we'll talk about the first law of thermodynamics. Okay. So see everyone then.